Non-deterministic process. In concurrent programming, deterministic and non-deterministic process can refer to how the execution of concurrent threads or process behaves in terms of predictability and consistency. These terms are particularly relevant when dealing with multi-threaded or parallel programs. Deterministic process. A deterministic process is the one in which the order of execution and the outcome of the program are predictable and consistent. In a deterministic program, the same set of input will always produce the same set of outputs, and the execution order of threads or process is well defined and consistent. Achieving determinism often involves using synchronization mechanisms such as blocks, semaphores, to control access to shared resource and ensure predictable execution. Non-deterministic process. A non-deterministic process is the one in which the order of execution and the outcome of the program are not guaranteed to be the same each time the program runs, even with the same inputs. Non-determinism can lead to issues like race condition, deadlock, and data corruption, as threads or processes may interact in unexpected ways. Achieving determinism in a non-deterministic program may involve introducing synchronization and coordination mechanism to make the program's behavior more predictable. This lack of determinism is often introduced by the inherent concurrency of the program, where the order of execution and the timing of events can vary. Now let us examine the two examples given here for the better understanding of non-determinism in concurrent programs. The first one is printing outputs. In this scenario, two processes P and Q are sending the outputs to a printer. The key point here is that as long as the output is not interleaved, it doesn't matter which process output appears first. The non-determinism comes into play because the order in which the output appears might depend on various factors such as scheduling of the process or the printer's behavior. From the user's perspective of the functionality of the program, it may not matter whether P's output or Q's output is printed first, as long as both the outputs are eventually printed. Therefore, the specific order in which these events occur is non-deterministic. The second one is reservation system. In this case, two travel agents P and Q are concurrently attempting to reserve the last remaining seat on a flight. Only one of them can get the seat, but it doesn't matter which one gets it from the perspective of the reservation system. The non-deterministic aspect here is that the order in which the reservation system processes their requests can vary. For example, if both the agents send a request at almost the same time, the system may arbitrarily choose the process one request before the other. Regardless of which agent's request is processed first, the ultimate outcome is that only one agent will be successfully reserving the seat. This outcome is non-deterministic because it depends on the timing of the request and the reservation system's scheduling. In both the examples, non-determinism arises from the concurrent nature of the program, which means that the specific order in which events occur is not guaranteed. However, the non-determinism doesn't affect the program's correctness or the end result. It simply introduces the uncertainty regarding the specific sequence of the events in a given execution.
What is mutual exclusion? Mutual exclusion refers to the concept of ensuring that only one process or thread can access a shared resource at any given time. It prevents multiple processes from simultaneously modifying or reading the same data, which could lead to the data inconsistency or corruption. Here is an example of mutual exclusion. Certainly, let's consider a different real world example of mutual exclusion. Think of a university lecture hall where a professor is giving a lecture and students want to ask questions during the class. To maintain the order and ensure that each student gets a fair chance to ask questions, a form of mutual exclusion is applied here. First step in mutual exclusion: request for access. In the context of mutual exclusion, threads or processes are analogous to students in the classroom. When a thread or process needs to access a shared resource or a critical section of a code, it initiates a request for mutual exclusion. This request is equivalent of a student raising their hand to express their intent to engage with their professor. Secondly, control unit. The control unit in the case of mutual exclusion is typically a synchronization mechanism, such as mutex, which is also called to be mutual exclusion, or a lock. These mechanisms serves as a professor or control unit, overseeing the access requests from the multiple threads or processes. They carefully manage the granting of access to the shared resource, ensuring that only one entity can access it at a time. Thirdly, one entity at a time. Just as a professor addresses one student's question at a time in the classroom, mutual exclusion mechanism ensure that only one thread or process can access the shared resource or critical section at any given moment. This strict control prevents simultaneous access, which could lead to data corruption and conflicts. Last but not least, queue of access request. In cases where multiple threads or processes concurrently request access to the shared resource, here a queue of access request forms. This queue, similar to the queue of questions in the classroom, ensures that access is granted in an orderly and fair manner. Threads or processes are served one by one, following the first come first served principle. This prevents conflicts by providing an organized order of resource access. Let's have a quick definition of what is critical section. The critical section is the part of the code where the shared resource is accessed, and it is essential to ensure that only one process can execute this section at a time. Failure to properly implement mutual exclusion can lead to data inconsistencies, deadlocks, and other issues that can cause program crashes or incorrect results.
Under the concept of safe access to shared data, we can see about safety as serializability. It is a fundamental concept in concurrent and distributed systems. For concurrency, the resources must be shared and their interleaving occurs. But in terms of safety, that do not provide much safety. So this safety is achieved by safety as serializability. First of all, let us see what is serial execution. It is the complete execution of one process before the other process begins. And this criterion produce safe results. Safe results means let us take two processes P and Q. Even though their order of execution changes, like P after Q and Q after P, and the both of the outputs are same, then for them serializability is possible. But in concurrent programming, when P is being executed and an expression from Q is inserted, their interleaving has taken place, which yields a different output. This is because both processes have some sort of shared access and their safety is a big question. This will not provide much safety. So then how is this safety is being achieved here? That is being discussed in the last point. Interleaved execution of processes P and Q is safe if it is equivalent to a serial execution. That is, we have already seen that in serial execution, even though their order of execution changes, their output is same. So, if the interleaved execution of processes P and Q follows the serial execution, then their output will be same and we can achieve that safety. So that is result must be same as that of a serial execution even though the two processes have interleaved. Next, let us see an example to know how the safety as serializability concept works.
So, hi friends. Hope you all understood what is safety as serializability. Now we will see an example based on safety as serializability. So, now let us consider two processes P and Q, and the computation values of P and Q are given below. We have to check whether the interleaved execution is safe and serializable or not. So, for the process P, the value of variable T is given as x, and the value of variable x is updated as t plus 1. For the process q, the value of variable u is given as x and the value of variable y is given as u star 2. Now we will move on to the solution. An interleaved execution is considered safe for two processes if the resultant outcome is equivalent to the outcome of some serial order of the process. For example, we can consider the same process. Like we can take two processes P and q, we have found a value after the interleaved execution, and um, we have to compare it with the values of x and y, that is uh, that we got after the execution of process p followed by q, and the process of after and or the process for q followed by p. If the value, if either of the value match the value that we have got for interleaved execution, we can say that the process of interleaved execution is safe and serializable. So now let us move on to the problem. So in first case, we are going to move into the case of order p followed by q. So always we have to initialize the value of x. And so after the execution of process p, we will get the value of t as 0 and value of x as 1. After the execution of process q, we will get the value of u as x and u as x, and so the value of u is 1, and we will also get the value of y as 2. Now finally we have got the value of x as 1 and the value of y as 2. This is the final value that we have got after the serial execution of p, that is followed by q. Keep this in mind, it will be useful in our future. Now let us move to the next case, second case. So in second case, we are going to execute process Q followed by the process P. So after the execution of process Q, we will get the value of U as 0 and the value of Y is also equal to 0. Now we will move on to the execution of process P. From the process Q, we have got the value of X as 0. So the value of T is also equal to 0. And we should also find the value of X. The value of X is given as T plus 1. We know that the value of t is 0, and so the value of x is 0 plus 1, which is equal to 1. So we can conclude that the value of x and y are equal to 1 and 0 after the execution of q followed by the process p. Now the last case, we will move on to the interleaved execution. So in interleaved execution, we are going to execute both the process simultaneously, right? So we will take a step of process Q and followed by the step of process P and vice versa. We'll move on till the end of the all steps. So in first step, we are going to take the step in the process Q. So in this process, we are getting the value of U as 0. And in next step, we are going to take the value of process P. So here we are going to get the value of T as 0. Now we will get a step of process Q. Here the value of Y will become 0. And now we are going to execute a process P. So here the value of X becomes 1. And finally we have got the value of X and Y, which is equal to 1 and 0. And if we remember, we have got the same values of X and Y when we have executed both Q and P simultaneously. Hence, we can say that this process is safe and, and serializable. So that why I have concluded that as the value of the variable after interleaving is equal to the values of the sequential execution of QP, we can conclude that the interleaved execution is safe and serializable in this case.